Okay, we're just going to cover one section today. It's kind of a bigger section, so I'll deal with that. It's the logic of quantified statements, Chapter 3. Start off with a definition. A predicate is a sentence that contains a finite number of variables and becomes a statement when specific values are substituted for the variables. The domain of a predicate variable is the set of all values that may be substituted in place of the variable. So, finding the truth values of a predicate. Take P of X to equal X squared is greater than X. Okay? With the domain real numbers. Okay, so you plug in values for the variables and try to find the truth set of the truth values of a predicate. So is the predicate true for P of 2? Yeah? Yeah. So P of 2 is true. What about P of 1/2? No, that would be false. So what about P of negative 1/2? Yes, it is true, because a quarter is greater than negative 1/2. So yeah, that's how you, so the truth set would be X less than 0 and X greater than 1. So if P of X is a predicate and X has a domain D, the truth set of P of X is the set of all elements of D that make P of X true when they're substituted for X. The P of X, the set of the truth set of P of X is denoted like this. So it is a set, so curly braces, X element of D such that P of X. That's how you define the set. Now the actual values can be written out in various ways. So there's that way, and then you could write out, say Q of n is the predicate, n is a factor of 8. What is the truth set of Q of n if the domain is z, integers? So what would the truth set be of n as a factor of 8? So it would be X is an element of Z such that X is a factor of 8. Set roster notation, though, would yield what? What are the factors of 8? And? And what else? Not 16. The domain is rational, or is integers. Yeah, the negative numbers. Forget about those, don't you? Yeah. So that is the truth set of that predicate across that domain. All right, let's see here. Now we have universal quantifiers. What is the universal quantifier? You can make a predicate a statement by assigning values to all the variables. That was done in the previous example. All those values in the truth set could be substituted for X to make a statement. -8 is a factor of 8, -4 is a factor of 8, etc. Another way to do this is to use quantifiers. Quantifiers are words that refer to quantities such as some or all and tell for how many elements a given predicate is true. The universal quantifier is denoted by the inverted A. It can be read as for every, or for each, or given any, or for all. So the sentence, every human being is mortal, can be expressed for all humans human beings X, humans X, X is mortal. Can also be written as for all humans, element of human, H is mortal. Definition for you. Let Q of X be a predicate and D the domain of X. A universal statement is a statement of the form like this for all some variable element of the domain, or for all of x element of the domain, and then the predicate is defined to be true if and only if q of x is true for each individual x in D. It is defined to be false if and only if q of x is false for at least one x in D. The value for x for which q of x is false is called a counterexample to the universal statement. So, say you have the statement for all of x, element of D, x squared is greater than or equal to x. D is 1, 2, 3, 4, or 5. Is this statement true? You have to go through all the elements to determine whether it's true, or find one as an example that it makes it not true. Yeah, it is true, because the squares are 1, 2, 4, 9, 16, 25. Those are all greater than or equal to 1, 2, 3, 4, or 5. Now you consider you change it to, for all of x, element of R, x squared greater than or equal to x. Is that true? No, it's not true. Why? Give me an example of why it wouldn't be true. When it wouldn't be true. 1/2. Exactly, 1/2 would be a good example. So if 1/2 is the counterexample. So that statement is false. Now the counter to the universal quantifier is the existential quantifier. The existential quantifier denotes there exists something. For example, there is a student in Math 140. There exists a P, denoted by the upside down E. There exists a P, which is an element of persons, people, such that P is a student in Math 140. To show that it's true, you only need to show that at least one element of the domain satisfies the predicate. makes the predicate true. So say we have there exists an M element of Z plus positive integers such that M squared equals M. Why is that statement true? Why would it be true? Yeah, positive in the domain of positive integers. But this statement is true, but why? What value for M makes it true? Equal a positive integer that's squared equals itself. Exactly. There you go. So all you have to determine that this is true, all you have to do is come up with one example as to why it's true. Because it's there exists is the quantifier. Now how about we do how about that one? No, that's not true. But to show that it's not true, you have to show that no element in the domain satisfies the predicate, makes the predicate true. So 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64. All of them make this false. Therefore, the statement is false. Now, as far as, we've been getting a little bit more thick into the use of symbols. The use of symbols like that is a formal representation of the ideas, mathematically formalizing ideas. It is important to be able to go between formal and informal language when dealing with mathematical problems. Take, for example, formally, for all x element of R, x squared greater than or equal to 0. What would be an informal way of saying that? Not using quantifiers, not using variables. How would you say that informally? No, without using variables. This is kind of from the first chapter quiz. Dealt with this a little bit. How about for every real number, its square is greater than 0? That's informal. Gets the idea across without bringing in variables or anything like that. Let's see here. How about, I'm sorry? Greater than or equal to 0? Yeah, that would work as well. For all x, an element of R, x squared does not equal -1. Yes, or no real number squared equals -1. Yeah. So how about with an existential quantifier? The plus, right? Yeah. The plus such that m squared equals m. Informally, that would be there's z plus is positive integers. So that would be there is a positive integer whose square equals itself. You see how that's informal? I mean, there's lots of different ways of saying it. That's just one way. For all positive integers, or no, for some positive integer, there is a number that equals itself squared. Yeah, like I said, there's tons of different ways of saying it. It just leave the variables out and use common language. How about the following statements using quantifiers and variables? How about all triangles have 3 sides? How would that look? For every triangle T has 3 sides. Yeah. How about no dogs have wings? There's a couple of ways to express this. For every dog, dog has no wings. Yeah. For all the element of dogs, D has no wings. Hasn't wings. unless they drink Red Bull. Anyway, there's another way to produce this as well. Same result. There exists dog, element of dog. Their dog has wings. And then negate it. There does not exist a dog that has wings. Yeah, that's where the not comes from. Let's see here. How about some programs are structured? Not the negation this time, because you're saying some. There exists some programs that are structured, such that the program is structured. Now, do you know what it means for a program to be structured? It's a style of programming that existed before object-oriented programming, which is what you write in C++ and Java and all that. Doesn't use classes, just uses functions. That's what a structured program is like. Anyway, how about universal conditional statements? Universal conditional statements. They take the form for all x, element of D, P of x implies Q of x. If P, then P of x, then Q of x. So just informally, how would you express for all x, element of R, if x is greater than 2, then x squared is greater than 4. No, that's formally. How would you express that formally? Informally, I'm sorry. For all real numbers, if they're greater than 2, the result their square is greater than 4. Yeah. You try to avoid using variables in informal language. But yeah, for all real numbers, if the number is greater than 2, then its square is greater than 4. Yeah. Yeah. Now, there are equivalent forms of universal and existential statements. Let's see here. Take the statement, take the two statements. For all real numbers x, if x is an integer, then x is rational. And for all integers x, x is rational. So, for all rational numbers x, if p of x, then q of x. P of x equals x is an integer, and q of x equals x is a rational number. Okay. So, this equivalent is, because of the restriction on the p of x, for all x element of z, q of x. You incorporate the domain of the first of the hypothesis into the universal quantifier and eliminate that predicate. So where z is a subset of R, consisting of all values of the variable x that make p of x true, there you go. You can write the equals truth set. The truth set of p of x is the domain of the second statement. Now let's see here. Let's look at two forms for the that are equivalent for all squares are rectangles. Okay. So for all x element of shapes, p of x, then q of x, where p of x is a square, and q of x X is a rectangle, yeah. Now, you can make the truth set of P of X the domain of X and make it X element of squares Q of X. Does that make sense? You're making the domain here the truth set of this predicate. Now, with an existential quantifier, let P of n be n is prime. Let E of n equal n is even, and take this following statement. There is an integer that is both prime and even. So the long way, there exists an n element of z such that P of n and E of n. Well, you can make the truth set of this into the domain. So there exists an n element of primes such that E of n. Equivalent forms, just use the truth set of the first element as the domain in the second statement. Now, bound variables and scope. Anybody here taking 119 right now? Yeah, you are. Okay, so, huh? Oh, you have yet to? Okay. Scope is very important in computer programming. It is where a variable has meaning. Consider the following two statements. For every integer x, x squared is greater than or equal to 0. Okay. And the second statement, there exists a real number x such that x cubed equals 8. Now, both statements use the variable x, but they serve different functions. We say that the variable x is bound by the quantifier that controls it, and that its scope begins with when the quantifier introduces it and ends when the quantified statement ends. So it's kind of like in functions where you use a variable in C++ in a function. Its scope is just in that function. Outside the function, it has no meaning. has no value. You can't access it. Same is true with quantified statements. So here, n is, these are, n is a element of integers. Here, n is an element of primes. So n has two different meanings here, here and here. They have different scope. So finally, we'll get to implicit quantification. Consider, if a number is an integer, then it is a rational number. It is a universal statement without the telltale word all, every, any, or each. The indefinite article a is the only indicator. So you got to watch out for informal language, what quantifier to use for a statement. It won't necessarily have all, every, any, or each. Might just have an a. There is a, in existential statement, there is a number that satisfies these conditions. A little notation here for you. If let P and Q, if P of X and Q of X be predicates, and suppose the common domain of X is D. P of X, big arrow, Q of X. That means that every element in the truth set of P is in the truth set of Q. Whoops. Oh. So the truth set of P of Q is a subset of Q. The truth set of Q of X. This can also be written out as for all X element of D, P of X, Q of X. But yeah, that it means that every element of the truth set of P of X is in the truth set of Q of X. So P of X is a subset of the truth set of Q of X. Now the double arrow is equal to the truth set of Q of X. They have identical truth sets. Or equivalently, whoops. So you can write it that way as well. But yeah, the truth sets are identical with the double arrow. And finally, for the day, I invite you to look at the slides at the tail end of section chapter 3.1 in the slides on Canvas. There's a program that was developed to help teach the principles of logic. It's called Tarski's World. I leave it to you to look at the slides on the computer. I would do it in class, but the way it's presented, it's a lot of back and forth between the slides with images and questions and that sort of thing. Kind of cumbersome to do in class, and I don't want to confuse you more than I already do. But you can take your time and look at Tarski's World on the slides for chapter 3, section 1. But that'll be it for the day. Have a good day. See you on Thursday.